Hello everyone, I Shishir Kumar on behalf of Midas IT welcome you all to this geostructural webinar series. This webinar is divided into two sessions. First session is related to structural engineering and the next session is related to geotechnical engineering. Since the two sessions have only 15 minutes gap, questions can be taken up only after the end of second session. So if someone wishes to attend the first session only, and if he or she has questions, then questions can be sent to us via email at the email ID displayed on your screen. With this information, I would like to begin the first session on box culvert and RC slab bridges. So this is how I am going to proceed. Firstly, I'll be discussing about box culverts, then RC slab bridges, and in the end, I'll discuss Midas solution to engineering challenges for box culvert and RC slab bridges. When we listen to the word box culvert, the first question comes to our mind is, why are box culverts so commonly used? The reason is, box culverts are ideal solution for drainage culverts with wide flow and low hydraulic head. They are very much suitable for difficult site conditions as installation requires minimum elevation and backfill. This is why it is widely used for underpasses, subways, outfalls, bridges, stream culverts, etc. In this presentation, we are going to see how Midas Civil handles box culverts. Midas Civil provides RC box culvert wizard using which finite element model of box culvert can be generated quite easily. We'll see this in the demonstration. Midas Civil can handle static analysis. Static analysis is for the loadings like earth pressure load, water load, embankment load and pavement load, barrier load, etc. Temperature load analysis can also be performed. That is the loading due to temperature difference between top and bottom of the deck slab. Moving load analysis can be performed. Midas Civil provides both 2D and 3D modeling. Over many years, engineers have been using 2D modeling for box culverts. And these days also many engineers are still using 2D modeling. But with increasing emphasis on finite element modeling and accurate results, the trend is shifting towards 3D modeling. In today's session, we will be discussing 3D modeling of box culverts. For 2D modeling, the model is generated in Midas Civil using beam and columns. And these beams and columns can be designed in Midas Civil as per the standard you desire, and the design report can be well obtained. For the 3D model, Midas Civil provides the design forces which can be obtained using local direction force sum or resultant force diagram. We'll see all these extraction options in the demonstration. For the demonstration, on the top right, you can see this is the box culvert which I'm going to model. In elevation, you can see this is the view. 26.3 feet is the width and depth of wing wall. Span of box culvert is 42 feet. Transverse length is 100 feet and skew is 5 degree and 30 minutes. I'll move to the software now to show the demonstration. This is how the start page of Midas Civil looks like. I'll open a new file. And as I said, Midas Civil provides a structure wizard for modeling box culverts. So we need to do nothing but just go to structure, RC frame or box culvert wizard. Here there are three tabs: longitudinal, transverse and loads. We will input the definitions and parameters for all these tabs. Firstly, for the longitudinal tab, we'll choose 2-dimension or 3-dimensional bridge. I'll choose 3-dimension. type of bridge is box culvert. I can define a material. I click on this box, click add, choose the material type as concrete. I can choose the standard out of all the standards available, and I can choose the material. Size of plate, this is the maximum size of plate elements in longitudinal direction. Wing wall can be considered, or you can choose to not consider this. Thickness of wing wall is specified here. I can also consider the curvature with the radius inputted here. I can consider convex or concave. Parallel or radial configurations can be chosen. Here the skew angle is specified, and all these dimensions can be inputted looking at this diagram. Next tab is transverse tab, where we define the transverse section of the bridge. In transverse, we can choose three types. Type 1 with barrier on both the ends. Type 2 with barrier and median. Type 3 with median on left position and barrier on the right. Likewise, we can input all these parameters looking at this diagram, and unnecessary parameters like these can be entered as 0. I can define support condition for box culvert, that can be general or compression only. I can choose what type I want, and this will define the stiffness of the soil springs model in the structure. Length of elastic link can be inputted here. Moving to the last tab, that is loads, I can choose the standard as per which I want to generate the load combinations. Then I can choose moving load code, let's say S12RFT, and click OK. The loads which can be defined in Midas Civil are self-weight, pavement load, soil surcharge with dry soil density and saturated soil density. The saturation is calculated based on the water level that we specify here. Barrier loading can be considered. Additional loads like noise barriers installed over the barrier can be considered as a separate load case. Sidewalk loading can be considered with the thickness and weight density, and the crowd loading on the sidewalk can be considered. Live load, I can choose truck or tandem or both, and this is eccentricity either left or right for lane definition. Temperature load is inputted from here. Shrinkage strain can also be considered, which is considered as a temperature load. And then we can save the wizard file by clicking on Save As. Saving the wizard file helps engineers model similar box culverts using the previously saved wizard file. For now, what I have done is, as per my requirement, I have already saved a wizard file. So I'll click on Open and open the previously saved wizard file. You see all the parameters are modified as per my requirement, and I can directly click OK. Let me undisplay the nodes for a better view. So this is the box culvert which is generated, and let's see the parameters which have been defined. It's a completely plate model, as I mentioned in the presentation. The material assigned is C4500, and the thickness is defined as per the input definition in the wizard. Editing the model is quite easy. Unlike any of our competitive software, once we generate the model from the wizard, we can edit it quite comfortably. Let's say I want to define the bottom slab with a different material. Then I can right click, add material, choose concrete, choose the standard. Let's say I want C4000, I can click OK, and I select the bottom slab and just drag and drop. So the material of bottom slab is changed. You see C4000 and C4500. for rest of it. So we can make changes as per our requirement after the model is generated. In some cases, box culverts also have piles modeled below the box culvert. For that, we can go to Node Element tab and use these CAD-based features for modeling the pile quite easily. Next, let's take a look at the boundary conditions. The wizard automatically defines boundary conditions as these. These are the fixed supports defined at the bottom, and these supports are connected to this structure using elastic links, which actually represent the soil. So let me show you the front view, and in this I can display the elastic link which connects the support to the structure. And there are point springs defined restricting the displacement in X. Let me hide the elastic links for better display. These point springs limit the displacement in global X direction, and this is for restricting the displacement in X and Y. We can make changes to the boundary conditions by going to Boundary tab and defining the supports as per requirement. The loads which are generated from the wizard are DC, that is dead load of culvert itself, along with dead load of components and attachments, like you can see dead load of barrier and sidewalk. The values displayed here seem to be quite small. Maybe changing the unit can, changing the unit we can see a better representation of the values. For now I'll just let it be US units. Like that, we have DW loading, that is dead load of wearing surface. Temperature loads are defined. This is with water, so saturated soil pressure considered on the side walls and the wing wall. This is unsaturated soil pressure. This is hydrostatic pressure. Hydrostatic pressure at bottom of the slab. Shrinkage load, which is applied as a temperature load, and the crowd load on sidewalks. Let me undisplay this. And then, so all these loadings which are displayed, if we want to check the loadings, then not only display, we can check the loadings in form of tables as well. So this is the table showing all the loadings that I have defined, all the pressure loadings actually. The good thing with this is I can copy the table, copy and paste it to Excel file where I can make changes as per requirement, and then copy it from Excel and paste it back in the software, and the changes will be considered. So that's a good Excel compatibility, helps you change the model quite easily. And if some additional loads are to be defined, then we can go to Load tab, Static load, Temperature load, Moving load. Any sort of load can be defined as per the requirement. So software defines the loadings which are quite common in case of box culverts. Let me undisplay the load, and then we'll take a look at the moving load. Software automatically defines 6 lanes which can surely be edited by going into properties, and we can edit these lane definitions. If we take a look at the lanes, then this is lane 2, lane 4. Likewise, it defines all the lanes on the structure. You can see all the lanes. Vehicles defined. Oh, it's asking for saving, so let me save it as a demo mode. Vehicles defined are tandem and truck vehicle, which we defined in the wizard. We can define additional vehicles by going into load, moving load, and adding the vehicles. We can add standard vehicle as per the standard, or we can also use user defined option for defining vehicles. and then moving load analysis can be performed. Also, there can be requirement of defining construction stages, but that's quite rare for box culverts, but you can surely click on this and click add. You can define number of construction stages that you want in the box culvert. Now let's take a look at the load combinations which are generated. There are two sets of load combinations generated, one up to 1 to 14, which is without considering the water. So this is unsaturated soil pressure, and next set is considering the hydrostatic pressure and saturated soil pressure. So we have two sets, and all the load combinations are generated as per ESTO LRFT 2002. If you want to make changes or define some additional, you can surely add load combination here, or you can go to auto generation, choose the standard as per which you want to generate load combination, and click OK. So load combinations will be automatically updated. For now, I'll just leave it to the previous load combinations and just click on run analysis. For analysis, Midas Civil supports 64-bit operating system supporting solver. That enhances the speed quite a lot because of no memory usage limitation. So larger the RAM you have, faster is the speed of analysis. Also, Midas Civil supports GPU accelerator, which can further enhance the speed of analysis by 3 to 5 times. And for that you require Tesla series graphic cards. So having that, you can further increase the analysis speed. Currently, I am running the analysis with 4 GB RAM, so the analysis would take roughly a minute or so. Let's wait for the analysis to be completed. The analysis is complete and it took around 111, so roughly almost 2 minutes. The analysis speed, as I mentioned, can further be increased. I have only 4 GB RAM, so analysis takes a bit of time. Comparatively, it's much quicker, and now we'll see the results. For that, I move to Results tab and go to Reaction, Reaction Forces or Moments. Here I can choose any load case or load combination for which I want to see the reaction. Let's say I want to see FZ, values, legends, click apply. The reactions displayed here are quite a lot because of the number of supports that have been defined. So for better viewing the results, I can click on this option which generates the tables, and these are the support nodes. I click select DW, or I can choose any other load combination as well and click OK. So these are the reactions at the point springs that are defined, and these are the reactions at the supports. The summation reaction can be seen at the bottom. Net reaction is in vertical direction, that is 154.98 kilopascals for dead load of bearing surface. Likewise, we can see deformation. Let's see the displacement contour. I'll choose a load combination, or let's say I leave it to load case DW. I can see DZ deformation. I don't want to see values, I want to see deformed shape, and click apply. So this is the deformed shape of box culvert due to dead load of bearing surface. If I want to see cutting line diagram for viewing the values, then I can use that as well. Let me activate a part of it for better viewing. So I activate only the top part of the slab, and now I will use plate cutting diagram. For that, I have defined cut lines. First line will be in longitudinal direction. Click add. Next cutting line I can define in transverse direction and click add and click apply. You can see maximum and minimum values are displayed here. For better view, I can click on reverse and click apply. If I want to see all the values, then I can uncheck min max only option and click apply. So all the deformations in longitudinal and transverse direction are displayed. If I want to see a graph, then I can check the graph option and click apply. So the graph for cut line 1 and cut line 2 deformations are generated. After looking at deformation, let's see the forces. We have plate forces or moments. Here I can choose load case or load combination, and I can see the values. I can choose the components. Let's say I want to check for MYY and I want the deform shape. Click apply. Let me activate entire box culvert. So this is the force result for load combination 19. But these force values are per unit length, so cannot be used directly for design. For using the values for design directly, we have several options. The first option is to use local direction force sum. To demonstrate this feature, I'll use fewer plates. Let me uncheck deform shape. For using local direction force sum and extracting the design forces, we can go to results tab and local direction force sum. I can use line select or polygon select. I'll use line here. I can choose a load case. Position, I can define one cut plane. Click calculate. The resultant force at this section is calculated considering the forces due to plates on the right side of that cut line. I can enter a name, cut 1. Likewise, I can define a cutting line in this direction. I can enter name as cut 2, click add. So you can see these forces are actually the resultant forces at the section. So these can directly be used for design. These results are not only displayed here but also as text output. So this text output shows you the local direction force sum results at cut 1 and cut 2. Also we can generate table output where I can select cut 1 and cut 2 and select any load case or load combination for which I want to see the result and click OK. So you see these resultant forces Fx, Fy, Fz and these moment values are displayed, which can easily be exported to Excel and used for design, or we can just copy and paste it in Excel. Not only this, along with these two cut lines, the results we saw just now were only for the selected load case or load combination in the text output. If we want the result for all the load combinations, then we can just click on all load case or combination. What this will do is, it will generate a text file considering cut line 1 and cut line 2 for all the load cases and combinations. So entire resultant forces are available here. The limitation with using local direction force sum is that the results are available at only the cut lines that we defined. And if we want the results at several sections to be displayed simultaneously, then that is not possible. For that, Midas Civil provides resultant force diagram. So we can go to forces, resultant force diagram. To use resultant force diagram, we'll need to go to pre-processing and Properties tab, Section for Resultant Forces. There are several modes: Structure Group, Polygon Select, Element Select. I'll use Polygon Select. Let me activate Whole Bridge, and then I can select sections. Let me activate fewer sections where I'll define the cut planes. I'll make the selection, and then I'll define the cut planes. First point, second point, third, fourth, and close. I have to define a direction vector that can be defined just by clicking at two nodes in longitudinal direction. Enter name cut1. Analysis results will be deleted. Yes. Then again define a cut plane on the second section. Enter a direction vector. Either we can use the mouse clicking for entering a direction vector, or we can directly enter the values in the box itself. Cut 3 and I click add. Now you see these virtual sections have been generated at which resultant forces will be calculated. And now I'll define virtual beam using these virtual sections. So I'll connect virtual section 2 to 3 and 4 to 5. Now you can see a virtual beam will be generated internally in the software, connecting this section to this section and 4 to 5. So in the results, forces will be displayed at this section and this section joined by a straight line. It will be more clear when we see the results. Let me run the analysis. And let me explain what I just did. I defined cut planes at 3 positions and defined 2 beams between the 3 sections. And now when I'll be checking the results at resultant force diagram, the results are displayed for virtual beams at both the ends of the beam. So results will be displayed at I end and J end of the first beam and I end and J end of the second beam. The advantage is, for calculating the force at, let's say, I end of first beam, it will use the resultant force of all the nodes highlighted here. And at J end, all these nodes which are selected in second section and I'm moving my cursor on will be considered for force calculation. And these forces can directly be used for performing the design. We'll wait for the analysis to be completed. So the analysis is complete, and let me activate the entire box culvert. I can go to results, forces, resultant force diagram, choose a load case or load combination, or let's say I want to see the moving load result due to load case MVL. I want MY results. I want to see the values and click apply. So you see I defined the 3 sections and the moment values due to moving load maximum are displayed at I end and J end of the beam. This is the maximum moment due to moving load, and I can choose MV minimum to see the minimum moment. I can also click on reverse to reverse the diagram. And not only this result can also be seen tabular view, in a tabular view, by clicking on this option. We choose the number of virtual beams, numbers assigned by 1 or 2, So I'll choose the both beams. I'll choose I and J ends, and here I can select any load case or load combination for which I want to see the result. Let's say I choose these and click OK. So you see these are the virtual beams, and all the axial load, shear Z, torsion force, moment Y and moment Z are calculated. All these are the resultant forces which can directly be used for the design of the box culvert. So let me show you. I can export it to Excel. After clicking export to Excel, I can save it, and the software saves the Excel file with all this table. I can open the Excel file now. So you see entire result has been exported to Excel, and I can use it for performing the design. I could also copy and paste the values to the table and use it for performing the design of box culverts. So you see how easy it is to extract the results from a 3D finite element model of box culvert. With this, I'll move back to the presentation.